So for this one, particle moves along the x-axis. We are given the velocity function, and we are also given an initial condition. The particle's at position x equals 2 at time t equals 0. So that starting point is something that you want to make sure that you have. Then it's asking, let's see. Let's talk about the concepts of these questions. Part A is asking, when is the particle moving to the left? Well, the particle is moving to the left when that's a question about velocity. So we are asking whether velocity is negative at those points. So we need to figure out whether that function and where that function in front of us is negative. Part B asks, write but do not evaluate an integral that gives the total distance traveled. Well, total distance traveled is a formula we should know. That should be an easy point. Part C, find the acceleration at time t. The biggest thing you need to be careful of when getting that acceleration is that you need to make sure that you have the chain rule, and then you're going to plug in 4. And then find our position at 4. We'll talk through how to do that. So, first off, to figure out when we're to the left, we also need to figure out where it's 0. So those are our points to figure out so that we can make a sign chart. That's going to be at t equals 3 and at t equals 9, because cosine is 0 at pi over 2 and 3 pi over 2. And so the places that will make it pi over 2 and 3 pi over 2 are at t equals 3 and t equals 9. And between 3 and 9 is when that velocity is negative. Part B, total distance traveled is the integral of the absolute value of velocity. That's a point. Either you got it or you don't. Notice it said, write but do not evaluate. So that means all you needed to do is write this setup. Part C, acceleration. Here's where the chain rule comes in. Derivative of cosine is a negative sign times derivative of the inside part. Derivative of pi over 6t is pi over 6. So a point for that acceleration function. And then we are looking at what is happening at 4. Well, we already know velocity is negative at 4. We figured that out in part A. Then it asks us, is the speed increasing, decreasing, or neither at time t equals 4? And what we see if we plug in 4, we really just need to figure out is it positive or negative. And if I plug in 4, then I get sine of 2 pi over 3, and that's in quadrant 2, and sine is positive in the second quadrant. So that means that our acceleration is negative. We already said our velocity was negative, so that means it is moving to the left, and it's getting pushed leftward by the acceleration, which means that we are speeding up. Speed is increasing because velocity and acceleration have the same sign. That should be your explanation. And then for part D, find a position at 4. The position at 4, if we have velocity, that means we're doing an integral. We are starting at -2, and then this will give me how far away from that -2 I moved in the time from 0 to 4. Point for the antiderivative, point for having the -2 as my starting point, and then a point for the answer. So there's your antiderivative. Antiderivative of cosine is sine. We have a pi over 6 that we would need to cancel because of the chain rule. So we need a 6 over pi in there. And then plug in 4 minus plug in 0. Plug in 0, we get out 0. Plug in 4, we get that sine of 2 pi over 3. We already figured out what sine of 2 pi over 3 was. So there is your answer on part D. So that's our process. Hopefully, everything there was kind of familiar and doable for you. The tricky part of this problem is that, first of all, we're given dB dt. So we have to think about this as a rate. It gives us an initial condition, again, that when I plug in 0, I should get out, when I plug in 0 for t, I should get out 20 for our weight. But the tricky part is that in dB dt, there is not a function in terms of time, like there usually would be. The function is in terms of weight. And so instead of plugging in our usual input stuff to get out our slope, we're actually plugging in to the output of weight and getting out rates that the weight is changing. So I'm putting in weights and I'm getting out the rates that the weight is growing. So let's talk through here. Part A. We are being asked in part A to compare when the weight is 40 and when the weight is 70. And is the bird gaining weight faster when we're at 40 or when we're at 70? So let's compare. At 40, that means that the weight is 40, so B is 40. And at 70, that means that the weight is 70. So we're going to plug in 40 for B, and we're going to plug in 70 for B. dB dt equals 1/5 times 100 minus 40. 100 minus 40 is going to be 60, and 1/5 of 60 is 12. So our rate that we are gaining weight when we weigh 40 pounds is 12. At 70, our dB dt, 1/5 times 100 minus 70. 100 minus 70 is 30. So 1/5 of 30 is 6. So when we weigh 70 pounds, our rate that we are gaining weight when we weigh 70 pounds is 6. So what is our winner? Our winner here is 12. So dB dt at 40 is greater than dB dt at 70. So the bird is gaining weight faster when it weighs 40 pounds than when it weighs 70 pounds. That's your idea on part A. That's the easy part. Let's move on to part B. In part B, we are being asked to find the second derivative in terms of B. So we're going to get a fairly easy answer, but we also are going to want it in terms of B. And we're asked, here's a graph, why can't B resemble the following graph? Okay. Let's look at that second derivative and see what it can tell us. Part B. Here's dB dt. Well, dB dB dt is also, a fifth of 100 is 20 minus 1/5 b. That might be a better way to write it in terms of finding the next derivative. Because, well, derivative of 20 is going to be 0, and the derivative of negative 1/5 b is going to be negative 1/5. But since we're taking a derivative of b, we need to write a dB dt. So derivative of negative 1/5 b is negative 1/5 dB dt. What is dB dt? Well, we have it sitting in front of us. Remember, it said define this in terms of b. So instead of just leaving it with the dB dt, we're going to plug in what dB dt is. What is dB dt? Well, it's 1/5 times 100 minus b. And so I'll do a little bit of more simplifying. Negative 1/5 times 1/5 is negative 1 over 25 times 100 minus b. So that is our second derivative. That's the first part of part B. The other thing in part B is that it asks us use that second derivative to explain why B cannot resemble the following graph. All right, here's our graph. Now, the thing to notice about this, if we're thinking about how on earth are we going to get anything from that graph, well, we need to think about what the second derivative usually tells us about a graph. Well, there's the original function in front of me, so the second derivative would tell me about concave up and concave down. That's the information that we can get from the second derivative. So if we have this graph in front of us, if we think about our concave up, remember concave up is a happy face and concave down is a frowny face. Concave up, starting at our 20, when we weigh 20, we start being concave up. We're still concave up until we hit about halfway through. We hit a point of inflection, and then we start going concave down the rest of the way. So it appears that we're concave up and then concave down. So there must be something in our second derivative that contradicts that. Notice it does not give labels for t because we don't need labels for t. Our second derivative is in terms of b right now. It's in terms of b. So we're looking at when I plug in 20 for b up to when I plug in 100 for b. From the interval of 20 to 100 for b, which is the area that graph is on, the second derivative well, let's see. If I plug in anything between 20 and 100, pick any value you want, I'm going to get 100 minus something less than 100. 100 minus something less than 100 means that we have a positive number here, but then we're going to multiply it by a negative 1 over 25. So we have a positive in the parentheses here times a negative is a negative. So B should always be concave down over this interval. B should always be concave down over this interval, but that graph says we're concave up and then concave down. So there is our contradiction. Again, this is a complicated problem. If we're not getting all of it right away, we're going to do more of these type of problems. But I wanted to look at and introduce this type of problem. We have part C left to go. And then we'll be done here. I'm going to start part C, and then I'm going to give you a couple minutes to try the rest of it. I'm going to get you started on it, so hopefully to a point where you know what to do from there. What part C asks is to use separation of variables to get our original function b. So let's take a look at that here. Use separation of variables to find b of t, particular solution, with the initial condition b of 0 equals 20. So I'm going to write that down. The b of 0 is 20. So when I plug in 0, I should get out 20. And so let's write in part C. We're going to start by separating out our variables. So that means this 100 minus b is going to get divided and moved to the other side. And then this dt needs to get moved over here. I'm going to leave the 1/5 on this side. I'll give you one more step here, and then I'm going to give you a couple minutes to try it on your own before I show the rest of it. Here comes our antiderivative. This is a process that should be familiar to you from last chapter. Antiderivative of 1/5 dt, right? This tells me what variable to put here. Antiderivative of 1/5 is 1/5 t. Antiderivative of 100 minus b of d 1 over 100 minus b means we have a natural log happening there. But because there's a minus b there, I need to undo the chain rule and put a negative out in front. So that when I take the derivative here, it would be 1 over 100 minus b times the derivative of the inside part would cancel out that negative and make it positive. And then, of course, I need a plus c there. So this is a case where I would get b by itself first, and then I would solve for your plus c. So I'm going to give you about a 2 to 3 minute head start before I show the rest of this. First off, I want this negative out of here, so let's move it to the other side. Negative 1/5 t. I'm dividing by negative 1, basically. A negative number is still a number. And now I'm going to rewrite. Our domain is up to 100. Up to a weight of 100, so these absolute value bars don't matter because b is 100 minus b is always going to be positive up to a weight of 100. So we're okay to get rid of the absolute value bars. And then here we have e to the negative 1/5 t plus c up in the exponent. And hopefully I can skip this step and you know by now that this c is going to jump out in front. It's e to the negative 1/5 t times e to the c, which is a big constant. C times e to the negative 1/5 t. Then I need to subtract 100 from both sides. Minus 100. And then I can divide by -1 to have b by itself. So my getting b by itself is that b equals, a negative number is still a number, so I still have c here, e to the -1/5 t. But I divided by a negative here, so instead of -100, it's going to be +100. One more step. We need to plug in our point and solve for c. Our point is that when t is 0, our weight is 20. So 20 equals c e to the -1/5 times 0 plus 100. C times e to the 0 plus 100. And so let's see. I need 100, and so let's see. I need -80. Subtract 100 from both sides. And then equals c times e to the 0 is 1. So c is -80. So our final answer will be -80 e to the -1/5 t plus 100. Five points when it was scored. A point for the separating of the variables, a point for getting the antiderivatives, a point for putting your plus c. So if you got this far, then that's 3 of the 5 points. And then the next points are getting b by itself and solving for c. Those two were a point apiece. Okay, so if you didn't get it all perfectly, there are still partial points to be had fairly easily on this problem. But this idea of being given dB dt in terms of the output like this is a pretty tricky problem, and we're going to look at a couple more that deal with those kind of problems.